Hey guys, so it's time to start looking at nice, normal, straightforward differentiation. So, if you've been taught it in the order of the book, you may have started with differentiation from first principles. Now if that's the case, you're probably thinking differentiation is a complete nightmare. However, differentiation from first principles, I would say, is probably the trickiest thing in this chapter. So now we're going to look at the more straightforward differentiation, which we use much more often than first principles. So in here we're going to look at differentiating single term functions where we have positive powers, negative powers and fractional powers, and then we're also going to look at finding the exact or the gradient of a curve at an exact point. So when you differentiate, you get an algebraic expression which is called the derivative or the gradient function. So this function gives a general expression for the gradient at any point on the curve. To find the numerical gradient at a given point, we substitute in the x value at that point. So first up, we're just going to be differentiating, and then for the second part of the video, we will be finding actual gradients at certain points. So let's crack on. Okay, first up then we need the rule. So if y equals x to the power of n, then dy by dx, our derivative, is equal to n times x to the power n minus 1. So what's happened here? The power comes down and multiplies the expression, and then the power goes down by 1. So it might look trickier than it is. Let's do some examples and convince you it's quite friendly. So here as well, I might mix it up with notation. I might use different ones now and then. So dy by dx we can also write as y dashed or y dashed of x. So you might see me writing that. That's just shorthand for dy by dx. Writing dy by dx all the time gets very tiresome very quickly. Okay, let's do some questions. Okay, first example. So y equals x cubed, and we want to find the derivative. So dy by dx is going to be, well, the power of 3 comes down and multiplies the expression. So we're going to have a 3. Then we're going to have x. Now what happens to the power is it gets reduced by 1. So we're going to have a power of 3 minus 1. So dy by dx is 3x squared. And that's it. Compare that to first principles. Look how simple that is. So again, the power comes down and multiplies the expression, and then also goes down by 1. Okay, second example. Y equals x to the power of 6. So dy by dx is going to be 6x to the power of 6 minus 1. So 6 minus 1 is 5. So it's 6x to the power of 5. Okay, next up, y equals 5x squared. So we've got a coefficient on the front, that's alright. So I'm going to use y dashed of x this time for the derivative, exactly the same thing as dy by dx. So the power comes down and multiplies the expression. So we're going to get 2 times 5x to the power 2 minus 1. So 2 times 5 gives us 10. So we got 10x to the power 2 minus 1. 2 minus 1 is 1. So we've got 10x to the power of 1. So we don't really bother writing the power. So it's 10x. Next up, f of x is minus 3x to the power 4. So here we would either say df by dx, or we could say f dashed of x. Both things are exactly the same, so I'm going to roll with f dashed of x. So that is going to be 4 times minus 3x to the 4 minus 1. Now 4 times minus 3 is minus 12. So we got minus 12x to the 4 minus 1. So that's going to be minus 12x cubed. Good times. Okay, let's see what happens if we have something like y equals 7x. So, remember here, differentiation is all about finding the gradient. Y equals 7x is a straight line, because our power of x is just 1. So if we think about this, straight lines have constant gradients. Their gradients never change. So in all the examples we've done so far, we've always had a higher power of x. So it's always been a curve. On a curve, the gradient changes depending where you are. So we're going to get a slightly different result here. So first of all, let's put a power of 1 on this x. Y equals 7x to the power of 1. So y dashed of x, our derivative, is going to be 1 times 7x to the power 1 minus 1. So 1 times 7 is 7. So we got 7x to the power of 0. Now, anything to the power of 0 is 1. So this is just 7. So what we've shown here, the gradient of this straight line, y equals 7x, is 7, which we already knew, really, hopefully. So straight lines, the gradient is whatever number is multiplying the x term. So we've just shown it here using differentiation. Okay, what happens if we try to differentiate a constant term then? So a constant with no variable, no x term. Well, so here we've got y equals 10. So we can think of this as y equals 10 times 1. Now, in the previous example, we just reminded ourselves anything to the power of 0 is equal to 1. So we could say here, we've got y equals 10 times x to the power of 0. So if we try and differentiate this, we would get y dash is equal to 0 times 10x to the 0 minus 1. But we don't really care about the rest of it. The important thing is we've got 0 multiplying it. So y dash is just equal to 0. So you would need to go through the workings there just to show you why when we differentiate constants they disappear. So you always get 0 even if we differentiated y equals 1 million with respect to x, we would still just get 0. So if you have no x term attached and you differentiate, the term disappears. Okay, how about differentiating something like this then? Y equals 1 over x. So what we need to do here is write this in its index form, so as a power. So hopefully you're alright with indices and you can quite confidently say 1 over x is x to the minus 1, like that. Okay, so if we differentiate that, we're going to get y dash is equal to minus 1 times x to the minus 1 minus 1. So we're going to get here minus x to the minus 2, like that. Now, that's it written as a negative power. We can write it again as a fraction. So x to the minus 2 means 1 over x squared. So this is equal to minus 1 over x squared. Okay, another one like that. Y equals 2 over x cubed. So first of all, write it in index form. So this is the same as y equals 2x to the minus 3. So y dash, our derivative, is going to be minus 3 times 2x to the minus 3 minus 1. So minus 3 times 2 is minus 6. And then we got minus 6x to the minus 4. So if we write that as a fraction, it's minus 6 over x to the power 4. Okay, what about then if we have something like y equals root x? How do we differentiate this? Well, again, we're going to write it as an index, write this in index form. So, remember, if you square root something, that's the same as setting it to a power of 1/2. So, we would first rewrite this as y equals x to the 1/2. Okay, so now we're going to differentiate. So y dashed is, well, 1/2 comes down. So we're going to get 1/2 times x to the 1/2 minus 1. So be very careful here. So we're going to have 1/2 x to the, well, let's do it step by step. So 1/2 minus 1. Now 1 in terms of halves is 2 halves. So we're doing 1/2 minus 2 halves as our power. So what we're going to get is 1/2 times x to the minus 1/2. 1/2 minus 2 halves gives us minus 1/2. Now, if we now turn this back into like square root notation and also fractional notation, we can say this is 1/2 times, well, x to the minus 1/2 means 1 over x to the half. So 1 over root x. And then we can just simplify that a bit and say it's 1 over 2 root x, like that. Good times. Okay, the last one here then for pure differentiation, and then we're going to look at finding the actual numeric gradient of a point on a curve. So, here we've got y equals 1 over root x. So, first of all, write it as a power. So, root x is x to the half, but it's on the bottom of a fraction, so y is x to the minus 1/2. So if we differentiate, y dash is minus 1/2 times x to the minus 1/2 minus 1. Now 1 is 2 halves. So we got minus 1/2 minus 2 halves. So this is minus 1/2 times x to the minus 3/2. Okay, so let's sort out the x term first. So we've got minus 1/2 times, right, well, x to the minus 3/2, first of all, is 1 over x to the 3/2. So we've got minus 1/2 times 1 over x to the 3/2 is saying x cubed square rooted. So we've got the cube root, no we haven't at all, we've got the square root of x cubed, like that. So now we can simplify it and say we've got minus 1 over 2 times the square root of x cubed. Good times. So it certainly got a bit tricky there towards the end. We were differentiating fractions and negatives, and then that guy, a negative fraction. Hopefully you found it alright. So now we're going to look at finding the gradient at a specific point on a curve. Okay, first example then. So let's say we want to find the gradient of y equals x squared at the point where x is equal to 2. So the first thing we need to do is differentiate to find the gradient function. So dy by dx is going to be, well, the power of 2 comes down, so it's going to be 2 times x to the power 2 minus 1. 2 minus 1 is 1, so we got x to the power of 1, which is just x. So our gradient function is just 2x. So remember, what that tells us is a general equation or function that enables us to work out the gradient at any point where we know the x coordinate. So if we want the gradient where x is equal to 2, all that we do is substitute x equals 2 into this. So the gradient when x equals 2 is, we should really write it as dy of 2 over dx. Now all that means is the value of dy by dx when x is equal to 2. So we get dy of 2 by dx is equal to 2 times 2, which on a good day is 4. So the gradient of x squared at the point where x is equal to 2 is 4. Let's do another one to show you how it changes. So we'll stick with x squared while we're here. So let's say we want the gradient when x equals 10. So we already know our gradient function is 2x. So we just find the value of dy by dx when x is equal to 10. So we get 2 times 10, which is 20. So the gradient of x squared when x is 10 is 20. Okay, example 2, so we want to find the gradient of y equals minus x to the power of 5 at the point where x is equal to 1. So, first off, differentiate. So, this time I'm going to use dash notation, just because it's easier. So, y dash of x is going to be minus 5x to the power 4. So that gives us our expression for the gradient anywhere on the curve. It's minus 5 lots of the x coordinate to the power of 4. So, to answer the question, we want the gradient at the point where x is equal to 1. We substitute 1 into y dash. So we write it as y dashed of 1. So y dashed of 1 is going to be minus 5 lots of 1 to the power of 4. Now 1 to the power of 4 is just 1. So we got minus 5 times 1. So it's minus 5. Good times. Okay, final example for this video then. So we want to find the gradient of y equals root x at the point where x is equal to 9. So, first of all we need to write the function in power form. So y equals x to the 1/2. So y dashed, our derivative, is 1/2 times x to the minus 1/2. Okay, so remember what happens there. The power goes down by 1. 1 is 2 halves. So 1/2 minus 2 halves gives us minus 1/2. So we did this one earlier. That gives us 1 over 2 root x. So we want the gradient at the point where x is equal to 9. So we substitute 9 into our derivative. So that's going to be 1 over 2 root 9, which is 1 over 2 times 3, which is 1 over 6. So the gradient of root x at the point where x is equal to 9 is 1/6. Okay guys, hope you found this useful. In the next video, we'll take a look at differentiating polynomials, so functions with more than one term.